Finally, we come to recursive ray tracing, and we'll briefly explain how that is implemented. Let me review what happens for mirror reflections and refractions. Again, I've shown the virtual viewpoint to the camera. The ray from that hits the scene, in this case the plane, and you generate a reflected ray in the mirror direction. In this way, you can get the reflections and refractions of objects by recursively calling the intensity function for the new ray. Here is the basic idea of recursive ray tracing, and essentially this is what has made ray tracing such a popular algorithm. You first trace the primary eye ray, you find the intersection, then you trace secondary shadow rays to all the lights, and if the shadow rays return unblocked, you apply the illumination model, otherwise it's zero. It's the V term we saw in the previous segment. Finally, you trace the reflected ray, and the color of the reflected ray will be the initial color from this calculation, plus the reflectivity times the color of the reflected ray. This is of course a recursive call, which it gives the recursive ray tracing name. Here is the recursive shading model. So the white parts of the shading model is what you saw earlier. It's really the green parts which I've added new, which is this KSIR and KTIT. The highlighted terms are recursive. So the first term, which is the case on subscript S, I subscript R, that is the recursive specularity or the mirror reflection. The last term is the mirror transmission. So if you hit a glass sphere, you reflect off it, but you also transmit into it. The latter term or transmission is not required in the homework assignment and is really extra. So what happens when you call IR is that that's a recursive call, because you have to now evaluate the intensity again using the same formula. So you trace the secondary rays for mirror reflections and refractions, you include the contributions in the lighting model. So the function, for example, that you may have, get color, calls ray trace recursively. Of course, recursion is one of the great inventions in computer science. It allows us to greatly simplify algorithms. It makes ray tracing so much simpler to implement in such a deep and elegant algorithm. However, recursion may go on forever, and so consider a hall of mirrors where reflected rays keep bouncing back and forth and they go on forever. A simple solution is to set a maximum recursive depth, for example 5, and so for each ray you keep track of how many times it's gone through the recursion. Once it's gone through 5, it does not spawn new recursive rays. If you implement transmission, then you have to take Snell's law and refraction into account, but transmitted rays similarly have a certain recursive depth. Finally, I'd like to talk about a couple of very simple add-ons that you can do with your ray tracer for fun. Again, not required in the assignment, these are really extra. You can of course do a whole lot of other things. Ray tracing is something that's addictive, and you can really go overboard and make a very nice image synthesis system. But I just want to talk about two things. So first, we've considered only point and directional lights, and in fact in OpenGL that's really all there is. But in a ray tracer, it's easy to consider an area light source. So consider a light source like this. What we do is we break it into a grid. So here I've shown one gridding of the area light. And in each of these grid cells, you can essentially treat it as a point light source. So by shooting, let's say 9 rays to various locations in this area light, you can replace the area light by 9 point lights. But one of the challenges if you do that is the shadows will have this jerky or quantized look where they suddenly jump from 0 lights visible to 1 light visible to 4 lights visible to 3 lights. So instead what one does is jittering. So within each of these cells or strata, one randomly jitters the location of the ray. So at one pixel it might be here, at the next pixel it might be here, and so on. This is something which is actually known as stratified sampling and is a very popular and useful concept. It can also be used for anti-alias images. So if you render your sphere and you really zoom in at the pixel level, you'll see the stair-step pattern. If you want to get rid of that, same idea. Instead of shooting a ray to the center of the pixel as an R solution, you shoot it randomly to a location in the pixel, again known as jittering. And that can be used to get rid of these jaggies and give a smoother appearance. In any event, area light sources and soft shadows is something which is easy to do using a grid of n by n on the light source. The second thing that's easy to do is more complex reflectance models. If you study computer graphics further, you'll see that the Phong model is not the end point of things. You have the Torrance-Sparrow model, you have other complex reflectance models, and that's easy to do simply by updating the shading model. However, the basic weighted ray tracing algorithm does have a limitation that we can only handle mirror reflection and refraction. There is a whole body of work that generalizes this to global illumination. Finally, I want to say that these segments that I've presented so far have introduced the very basics or very foundations of computer graphics. Beyond this, there are many exciting topics that can be considered, and I would encourage you to go to my website where I have links to the Advanced Computer Graphics course at UC Berkeley CS283, as well as some of the later segments in CS184 that cover more advanced topics in rendering, and CS283 goes into topics in modeling, topics in animation, topics in simulation. This is just the start of an incredible journey in computer graphics that I hope you have.